In this section, we're going to review the material and characteristic values or eigenvalues that you would have learned in 822. This includes what the definition is, how to compute an eigenvalue, how to compute the eigenvector, as well as a theory about when a linear transformation is diagonalizable. This theory connects to the null space or the geometric multiplicity of the eigenvector, as well as the eigenvalue, as well as the algebraic multiplicity of the eigenvalue. To start, we're going to review the definition of an eigenvalue, eigenvector. If we let V be a vector space over F, and we let T be a linear operator, so it's mapping a vector space to itself, then C in our field is a characteristic value or eigenvalue of T if a non-zero vector alpha in our vector space V exists such that T of alpha equals C alpha. The vector alpha is called the characteristic vector or eigenvector of T. The characteristic space or eigenspace for a characteristic value is the set W equaling to alpha in V such that T of alpha equals C alpha. Now we can show that the characteristic space is a subspace of V, as the name implies. And we're going to leave this as an exercise. Okay, and recall that this is a subspace defined using T. Now, one thing that we have is what is the characteristic space of a, or how can we determine the characteristic space or compute the characteristic space for a specific value? Well, the characteristic space for C is equal to the null space of T minus Ci. What this means is if I know how to compute the null space of a linear operator, I can compute the characteristic space. This is very useful because we do know how to compute the null space. We do know how to compute the kernel of our linear transformations. And this is true because T alpha equals C alpha if and only if T alpha minus C alpha equals 0, if and only if T minus Ci of alpha equals 0. So we're in the null space of T minus Ci. This gives us a clear process for solving for the characteristics of, or the characteristic spaces of for a specific characteristic value. But now we got to determine, how do I compute the characteristic value? Well, the characteristic values for T are precisely the value C such that T minus Ci is not to 1. That is to say, the determinant of the matrix representation of T given a basis beta minus Cin equals 0. This means that to find the characteristic values for T, we must solve for the roots of the characteristic polynomial. F of x equals the determinant of xi minus t beta, or xi minus a, where a equals t beta, is any matrix representation of t. Now, here you'll notice it's slightly different than the definition we used in A22. Instead of having lambda at the back, we have x out front. And this is because the polynomial that we create now will always be monic. The leading term will always be 1 instead of it being -1 and 1. Now, when you're doing your homework, if you're determining what the characteristic values are and you want to do a minus lambda I, that's perfectly fine. The only thing here is that by using this definition, we always have a monic polynomial. The leading coefficient will always be 1, which theoretically is much nicer. So the reason for this here is it is theoretically nicer. So if we look at t, which maps r to r squared to r squared, be represented using the standard basis, we have a equals 0, -1, 1, 0, then let's compute the characteristic values. Well, the determinant of x minus, or xi squared I2 minus a equals the determinant of x1 minus 1 x, which equals x squared plus 1. Well, what does this mean? This means there are no real roots. Now, this implies that there are no eigenvalues because we're going from real to real. Now, if t was mapping c squared to c squared, and it was represented by a, then t would have 2 characteristic values. Because the determinant of xi2 minus a equals x squared plus 1, which equals x minus I, x plus I. Thus, the characteristics are x equaling, or lambda, or we should say c equaling plus or minus I. We have complex characteristics. Okay? In some cases, we care about whether we care that we're specifically going from real to real, and in this case, there would be no eigenvalues. Where in other cases, we like going from complex to complex using real matrices. So we're okay with the eigenvalues being complex. We just, our matrices are defined just using real entries. And that depends on what your situation is. We now look at a more complicated example, a 3x3 matrix. So f of x equals the determinant of ax cubed minus a, which equals the determinant of x plus 9 minus 4 minus 4, 8, 16, x minus 3 minus 4 minus 8, and x minus 7. Okay? Now, if you compute your determinant, what you're going to find is you're going to find that this equals to x cubed minus x squared minus 5x minus 3. And we're going to leave this as an exercise for you to work through. And it has to do with computing the determinant of the expression. So we have f of x equals this. Now, we would like to factor this. A lot of people jump into factoring by trying to figure out what number divides. And they try to just factor it. But with cubics or anything higher, my suggestion is plug a few numbers, and specifically plug the factors of my last term. Okay. There's a reason why the factors of this last term will help. So what I'm going to do is I'm going to try a few different terms. I'm going to try f of 1, f of minus 1, f of 3, and f of minus 3. My goal is to be able to factor to the point that I have a quadratic function, because when I have a quadratic function, now I have a technique to factor. So I'm going to try f of 1. F of 1 equals 1 minus 1 minus 5 minus 3, which equals minus 8, which does not equal 0. So this is not a factor. Now I'm going to try f of minus 1. This equals minus 1 plus 5 minus 3, which does equal 0. Thus, x plus 1 is a factor. Now I'm going to try f of 3, which is 27 minus 9 minus 15 minus 3, which equals 18, 3, 3. This equals 0. Thus, x minus 3 is a factor. And if I apply minus 3, I get minus 27 minus 9 plus 15 minus 3, which equals 3 minus 24, which does not equal 0. Thus, x plus 3 is not a factor. Now, I could have stopped once I got one factor, but I got two factor. And now what we're going to do is we are going to divide out our characteristic polynomial by one of these factors. And looking at this, I like dividing by x plus 1 because it looks nicer. So I'm going to do x cubed minus x squared minus 5x minus 3 divided by x plus 1 gives me x squared, x cubed plus x squared minus 2x squared minus 5x. This means I get minus 2x squared minus 3x, or minus 2x, leaves me with minus 3x minus 3 minus 3 minus 3x minus 3 equals 0. If we did this calculation correctly, we're going to get a clean factoring. So this implies that f of x equals x plus 1 times x minus x squared minus 2x minus 3. We know that x minus 3 is going to be a factor, so we could factor out x minus 3 here. Or we could do our factoring of quadratics. Either way, what we're going to get is that it's going to be x plus 1, x plus 1, x minus 3, which equals x plus 1 squared times x minus 3. So we have the prime factor x plus 1 twice, and we have the prime factor x minus 3 once. We're now going to solve for the characteristic spaces for c equaling 3 and c equaling minus 1. And to do this, we're going to solve for the solution space to the homogeneous system of equations, 3 minus a set with 0, or represented by 3 minus a 0, and minus I minus a with 0. Now we're going to zoom in to kind of help give us some space. So once we solve for that solution space, we'll talk about how we can take this solution, a basis for the solution space, and create a basis for the characteristic space. So we start with 3i minus a being 0. So this should be 3i. So it's clear what the identity function is, or the unit function is. And now here, this augmented matrix is equal to 12 minus 4 with 0, 8, 0, minus 4 with 0, 16 minus 8 minus 4 with 0. Now, if we do a bunch of row operations, we'll eventually get to the row echelon form of 1, 0, 1 half, 0, 0, 1, 1 half, 0, 0, 0, 0. Okay. Now, let x1, x2, x3 be a solution to the system x1 plus 1 half x3 equaling 0, and x2 plus 1 half x3 equals 0. Here, we take our free variable and we let it be free, so we're going to let x3 equal s, an element of the real numbers. Thus, x1 equals minus a half s using our first equation, and x2 equals minus a half s using our second equation. Therefore, x1, x2, x3 equals minus a half s minus a half s, which equals s times minus a half 1.
Therefore, the set minus a half, 1 is a basis for the solution space. So the question is, how can I take the basis for the solution space and convert it to a basis for our characteristic space? And to do this, we're going to use the basis that was used for our matrix representation. And if we look back, our matrix representation, we're representing a linear transformation R3 to R3 using the standard basis. This means my basis is going to be E1, E2, E3. So to convert back, what I'm going to do is I'm going to take these scalars and multiply them by the basis vectors E1, E2, 3. Thus, the set 1 minus a half E1 plus minus a half E2 plus 1 times E3 is a basis for the characteristic space. That is the set minus a half, 1. Now, it might look, wow, they're the exact same, but the only reason that's true is because the solution space are vectors in R3, and our vector space was R3, and we use the standard basis to create our matrix representation. If our vector space had been some other vector space, or we had used a non-standard basis to create a matrix representation, the solution space would not have been the same. So let's compute the characteristic space for characteristic value -1. Again, we have the same setup, minus a, minus a equals 0. This leads to the system of equations 8 minus 4 minus 4, 0, 8 minus 4 minus 4, 0, 16 minus 8 minus 8, 0. Doing some row operations, we get to the reduced echelon form of 1 minus a half, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Let x1, x2, x3 be a solution to the system x1 minus a half x2 minus a half x3 equals 0 equals 0. Now with this solution, or with this system of equations, we have two free variables, x1 and x2, or x2 and x3. So we're going to let x2 equal s, an element of the reals, and x3 equal t, which is an element of the reals. The reason why they're element of the reals is because our field is the real numbers. Then, using our system of equations, we can see that x1 equals a half s plus a half t. Therefore, x1, x2, x3 equals a half s plus a half t, st, which equals s times a half 1, 0 plus t, a half 0, 1. Thus, the set 1 half 1, 0 with 1 half 0, 1 is a basis for the solution space. Again, we're going to use the same technique to convert our basis for our solution space to a basis for our characteristic space. Therefore, 1 half E1 plus 1 E2 with 1 half E1 plus 1 E3 is a basis for the characteristic space. Now this set happens to equal the set 1 half 1, 0, 1 half 0, 1, which was our original set. But again, that's because we use the matrix representation in the standard basis. And we use that nice set. Now, now that we've gotten our two bases, let alpha 1 equal the vector minus a half, 1, which was our basis vector for our characteristic space. Lambda c equals 3. we're going to let alpha 2 equal 1/2, 1, 0, and alpha 3 equal 1/2, 0, 1. Now, notice that if we let beta equal the set alpha 1, alpha 2, alpha 3, we actually get a basis for R3. Well, also, there's something interesting about this basis. If we apply t to alpha 1, this is 3 alpha 1 because it's an characteristic vector for characteristic value 3, which equals 3 alpha 1 plus 0 alpha 2 plus 0 alpha 3. Additionally, t alpha 2 equals minus alpha 2, which is 0 alpha 1 plus negative 1 alpha 2 plus 0 alpha 3. And t alpha 3 equals minus alpha 3, which equals 0 alpha 1 plus 0 alpha 2 plus negative 1 alpha 3. Thus, it follows that t is diagonalizable. That is, t, the matrix representation of t in this basis is the matrix 3, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Whereas the matrix representation of t in the standard basis, E1, E2, E3, is not. This equals A, which is not a diagonal matrix. So while there is a basis where it is a diagonal, not every basis forms a diagonal.